I'm going to give quite a broad overview of the type of work we do on integrating geospatial data sets, including mobile data in many cases, for estimating population distributions and dynamics. So we're a group at the University of Southampton very much focused on developing new methods for integrating data sets to try and fill gaps, make more timely, more small area population data, have quite a focus on low middle income countries, but also do a lot of work globally, some of which includes the UK. There is a strong interest in having up-to-date, reliable, small area demographic data, and that underlies so much about decision-making, governance, equitable allocation of resources. But there are challenges all over the world, starting with the basics of some countries have not done a census for decades. There can be a lack of complete registry administrative data systems to fill those gaps, to produce updates in intercensal periods. And COVID has caused a disruption to many countries' census plans. Plus, even when we do a reliable census every 10 years, there can be high spatially varying fertility rates that are hard to predict. There can be migration patterns that change those numbers subnationally. Some countries have significant rates of displacement. And then, of course, across the world, there is this seasonal routine, all kinds of mobility going on that change our population numbers all the time. So what we try and do in WorldPop is firstly to try and get that basic population distribution at small areas, is to try and build up a picture of the landscape. We can't count everybody all the time, every minute of every day in every place, but we can nowadays capture some of the characteristics through geospatial data sets. So it looks more like this. And the types of data we're thinking about for, first of all, the basics of population numbers, the residential population, are things like the location of infrastructure, points of interest, mapping buildings and their heights from satellite imagery, processing those buildings to identify things like neighborhood types, looking at pictures of the Earth at night to understand electrification, the presence of humans, and then getting all of these kinds of data sets at multiple time points to try and understand the changes in human settlement patterns. So this is a starting point for us trying to get population estimates. And this then feeds into spatial demographic models where we are using some form of population data that we trust to benchmark or as training data for a model, some form of settlement data to tell us where there is human habitation and where there is not. And then geospatial data sets tell us something about how those population densities vary spatially and temporally within those settlement areas. These feed into spatial statistical models to produce estimates at grid square scales and ideally with measures of uncertainty around them. And there are two broad approaches depending on the type of data that are available. If we have population data at an aggregate level that we trust, we can make use of the geospatial data sets to disaggregate that data to the grid squares to get smaller area estimates. So an example of this is where we have population counts at an administrative level. These may be 10,000 in each one of these units, and it's difficult to use that kind of data to integrate with things like location of health facilities to look at access patterns, or to be able to integrate with ecozones that are measured with different boundaries. But we do have these geospatial data sets that tell us something about the distributions within there, whether it's the nighttime lights, whether it's land cover, and it's the building footprints derived from satellites. And so what we do is build machine learning based models to learn the relationships between these densities at the core scales and these higher resolution geospatial data sets to ultimately produce predictions at the small area scales. This is something that's very scalable. If you have population data at these subnational scales across the world, we can apply these models to produce gridded estimates across the world. And these are used in various portals, and some of you may be familiar with these types of data. They're available at subnational scales, 100 by 100 meter grid squares, and by age and sex structures. But often we don't trust that data at the administrative unit level. As I've said, there can be a long time between censuses. Things could change, populations can move, and maybe all we have that we trust are small area sample data from a recent household survey or a census that was incomplete and there are gaps within it. And so the second type of approach is then using the relationships between the population data that we have in the small sample areas and the geospatial data sets to build a model to predict population densities in those grid squares. And these are often bespoke models dependent on the situation, but make use of geospatial covariates to produce population estimates. I won't go into the details of this today because I'm more focused on the mobility, but these types of approaches now are starting to be adopted in multiple places, whether it's filling gaps in the census in Colombia, producing estimates for vaccination planning in Nigeria, the census planning in terms of delineating enumeration areas in Benin, official statistics in South Sudan, preparation for the census in Cameroon, preparation for census in Thailand, and then intercensal estimates in Papua New Guinea. These types of approaches are starting to be used where there are sparse data or there are just challenges in being able to collect and undertake a census. And it's not just population counts. These type of approaches can be used with household survey data to produce proportions under 5, vaccination coverage, female literacy rates, poverty rates, to build up an atlas of estimates in a situation where a census cannot be undertaken or has been a long time since a census has been undertaken. So the challenge, of course, is that we get to that baseline of residential population totals and characteristics, but then people move around. And this causes obviously challenges in measurement. And there's been traditional data sources to try and capture those changes, whether those come from a census asking questions about migration, cross-border traffic surveys, commuting surveys, household travel history surveys. But now there are also these newer forms of data coming from smartphones, coming from geospatial data sets that vary temporally, coming from shipping statistics, mobile phone data, and personal GPS. And WorldPop, this involves then adding to this stack of data. So whether it's a partnership with Google to look at the proportion of Android devices moving between grid squares, using data produced from the Meta Data for Good program to estimate changes in Facebook users, or working with mobile phone companies using call detail records. And on top of that, trying to explore other types of geospatial data that are correlates of how populations move, whether that's connectivity from road networks, it's vegetation changes in agricultural societies that drive seasonal changes, or it's capturing those urban and rural locations that are the drivers of commuting and seasonal changes. And this enables us to try in some countries to estimate population characteristics better, measure migration, and then map those distributions more dynamically. So the population characteristics, we often have a situation where for a country that is estimating their rates of poverty, there are household survey teams that will go out and collect samples in one area, one neighborhood and another neighborhood, producing this kind of picture across a country. That only gives an estimated poverty rate for very small areas, small samples. And it looks something like this. But through a range of academic studies, there's been conclusions that it tends to be in the more remote locations, there are higher rates of poverty. It tends to be in the more urban areas, there are lower rates of poverty. And those areas that show greener areas tends to be higher rates of poverty and more rural, more agrarian. Higher nighttime mobile use have higher rates of poverty. Mobile data spending with lower rates of poverty. So there's this set of relationships that have been explored across the literature. Each one, when we have these geospatial data sets that can measure some of these things, can provide us with covariates. So we can measure that remoteness, that distance to roads, or the brightness of nighttime lights to infer rural and urban locations, the amount of vegetation in terms of those more agriculturally drives communities. But also with the mobile data, we can process these kinds of data to look at the percentage of calls that are made at night, the amount spent on weekly top-up, and the amount of mobility that occurs in different locations. And when we bring those together in the same kind of geostatistical models as the population estimates to learn those relationships between wealth in this case and the geospatial data sets, we can produce these predictions of wealth index, which do pretty well, not perfect, and therefore it's important often to measure that range of uncertainty in those outputs and communicate that. So a second component can be trying to come up with estimates of migration. Often countries, when they are conducting a census, will also ask questions about where did you live a year ago or 5 years ago? And here's the results of that report for the Namibia 2010 census. So we are interested, can we use these mobile phone call detail records that can tell us about how mobile phones and their users are moving at the data collected at similar timescales as the census to measure those ongoing changes in migration patterns and flows? Well, firstly, when we just look at the correlations, it's pretty strong. The number of people moving and changing residence across the course of a year compared to the number of mobile phones that are moving is pretty strongly correlated, but you see on those axes that actually the number of phones moving is far higher than the number of people. So not so useful for trying to estimate numbers of people changing residence. So here we tested a set of different models, some of which were just using the mobile phone data as a linear model, linear scaling to match the migration, but others used different sets of geospatial data sets, including proportion of urban, proportion of population living in urban areas and the origins and destinations, distances between locations and travel times between locations. And when we start to bring in these geospatial data sets, we can do pretty well in terms of estimating those movements of people in this type of statistical model, both the outflows, inflows, and the net flows. It's hard to visualize in a quick slide, but those patterns then look pretty similar between the census and the model based on the call detail records and the geospatial data. And the value, of course, is then we can have some confidence in being able to update those migration statistics across years in terms of understanding flows and changes year to year. So finally, I'm going to talk about trying to estimate those distributions. This is now quite an old video, but as a paper we did a few years ago looking at phone data that we had at the time of the French census and trying to understand, is there a simple model that can translate the density of phone users into the density of populations from the census? It turned out a pretty simple model could do that across France, where phone user densities were pretty consistent across the country. And of course, the value here then is that just like in the migration statistics, we can start to use that model to push forward in time and to look at changes in intervening periods and intervening days. So here we were able to look at those patterns and see what was going on in France in terms of the changes that happen in a typical week: Monday, Tuesday, Wednesday, Thursday, Friday, and then disappearing out into the vineyards and the coast. And then as the holiday period comes along, people obviously going to the coastlines and the cities emptying out. This was interesting for France. We were more interested in trying to apply this for countries where there is much more sparseness in official statistics and data. So testing these kind of approaches, firstly with WHO in Namibia, looking at the population density changes in this case from December to January, seeing huge amounts of people leave the city, go back to the rural areas in the north where they often had families still, and then reverse back again in January. And those fluctuations occurring throughout the year. Of course, the interest in someone like WHO was to understand how did that change demand on resources. So understanding the changing populations in catchments within the country. And then COVID came along and we also started working with similar types of data, but this time the number of Facebook users as opposed to the number of mobile users with Data Science Campus and Facebook in the UK, and a similar type of analysis in terms of the changing population numbers, in this case in London, as the 3 different lockdowns and summer patterns came along. And also understanding those changes and those movements that occurred across and between regions in the country, enabling this kind of data was produced each day, so it enabled an update each day as things went along. It also enabled us to tackle questions like this one in terms of regional policies. Could we analyze and see how successful those might be and what could be done? So this involved looking at data from Google that had a normalized proportion of mobile phones moving across Europe, but also then a data set from Vodafone that had absolute numbers of mobile phones using, and then building a model that could translate one to the other, so we could get an estimate of probabilities of moving between locations for each 8-hour period. And the value here is to try and look at those dynamics. If we had districts or regions and there were infected people in orange, We close down one, but there are still people who are infected in others, and that spreads. And you close down another one, but that other one, the one that was originally locked down, people have recovered. But people are moving all around, bringing those infections in, etc., etc. So we could build a model using these types of data, a susceptible, infectious, recovered type model at the district level, and then use the movement data as a way to measure that movement rates between those different regions. And this enables us to get some insights about how different lockdown measures are impacting across the continent. So if one country ends its lockdown early, we see that actually it impacts the entire continent in terms of the time available to vaccinate more people. Has a significant variance in terms of the countries that are much more connected than others. We see Europe and the UK pretty well connected to the rest of Europe, and so a bigger impact if they end their lockdowns earlier. We see the situation if countries and regions could coordinate their interventions. We see the number of infected drop away much faster than if we're all doing different things at different times. So I'm finally going to just highlight what can we do if we don't have full detail records and smartphone usage is low. So this is the situation that often occurs with some of the lower income countries, Namibia here, Kenya, Pakistan. Whenever we look at the call detail record data, we see some significant fluctuations in terms of seasonal movements of populations. So how can we measure and characterize that if we don't have data from call detail records, if we have smartphone data, but we know that there are huge numbers of the population that are not using that kind of data? So this again is where we bring in these geospatial data sets. So firstly, call detail records can help us validate and train a model, but we want to try and capture some of these things that are driving the seasonal patterns. So whether it's vegetation amount and an agricultural society that determines the movements of agricultural populations, it's the mapping of urban and rural areas to determine those push and pull factors. It's the timing and location of public and school holidays that are often a big driver of seasonal movements. And then some of these smartphone movements, though they are very biased and full of gaps, do give some indication of relative connectivity between regions. And then finally, data sets that do change temporarily, things like the night lights, indicate things like the movement of seasonal populations into urban areas, turning on lights, lighting fires. So bringing these all together, again, in a geospatial model to try and build on the weaknesses and strengths of each, to estimate, in this case, the change in mobility for district I and month T. We tested this, and this is a difficult one to understand, but the further that distribution is from the line, the stronger that covariate was in describing the seasonal changes in mobility. So we see things like the timing of the holidays, rates of poverty, urbanicity, in this case testing for Kenya, explaining some of those seasonal movements quite strongly. And this gave us confidence then to test and expand these kinds of models across different subnational regions, to, in this case, looking at mobility change in July relative to a January baseline, and helping us to move beyond those static pictures of population distributions. So I'll finish here, but just a few messages that obviously timely and accurate small area population data are pretty important for equitable, resource-efficient decision-making. But we don't have the resources to count everyone, everywhere, all of the time. So these geospatial data sets from satellites, surveys, cell phones can help capture some of the correlates and drivers of population distributions and dynamics. But we have to be careful. These data are often biased, incomplete, and tied to specific scales. So by linking them together by geography, geographical regions, small areas, it does offer a framework by which these different forms of data can be integrated to draw on the strengths of each, to account for bias, and to tailor to specific questions. And ideally, undertaking this with stakeholders is pretty vital to ensure that those methods are actually going to be adopted and sustainably used. Some of the data sets I presented are available on our website, things like the timing, locations of holidays, the connectivities in Namibia, air and traffic statistics, migration estimates. The COVID analysis is also available, and there are many training materials on some of the population modelling I presented. So I just acknowledge that this is part of a much wider team at WorldPop, and leave this on the screen because much more details are available in these papers I've presented.